The first speaker of today is Kateryna Tatarko, and she will talk on isoperimetric problem from classical to reverse.
Thank you. So I'll continue. So what we've seen yesterday. So yesterday we talked about the main theorem that I announced in the first lecture, but on the plane. So today we are going to deal with it in R3. So as before, we're going to look only at one convex null polytopes. So really intersections of balls of radius 1 in R3. And I'm going to show that if the surface areas is the same as the surface area of the lens, then if the surface areas are fixed, then the lens has the smallest volume. So again, based on the approach in R2, so on the plane, we could see that a big chunk of that process was independent of the dimension, didn't really depend on the plane. And we are going to base the three-dimensional case on the same reasoning. So our approach here is again based on the formula that we got last time, that the volume can be written as the integral over the layers, and these layers are represented by surface areas of the inner parallel bodies. Okay. So as before, our goal, so we want to show that locally the surface areas of inner parallel bodies really satisfy this inequality around t is equal to 0. And last time we showed that this is enough to claim that then the surface areas possess the same inequality on the entire interval, the entire interval from 0 to R3. So this is exactly what we want to do here. And the idea is the same. So in order to compare them, what we want to compare their derivatives at 0. If I know that their derivatives at 0 satisfy this inequality, with the assumption of the theorem, I can get that the functions also satisfy the same inequality. In order to compute derivatives, I need again to find how the surface areas looks like. And again, the idea is similar. So the first what we want to find the surface area of the inner parallel body of K. So now the situation gets a bit more complicated, as we are not anymore dealing with just curves on the plane. So with the curves on the plane, we had only circles, intersecting circles. So in some sense, the combinatorics was a bit easier than what is going to be here. Now I'm going to look at this one convex polytopes. So now I'm taking the spheres of radius 1 and intersecting spheres. So of course the combinatorics is going to get a bit more complicated. I will now get some facets, so some portions of the sphere. I will also get the edges where the spheres intersect. And I will also get the vertices where the sphere intersect. I might get, right? So it depends on how many balls I'm taking intersection. So let's introduce some notation here. So let's focus again. Let's say that I have two spheres, two adjacent spheres intersect. So I'm going to denote, as before, by beta i's area of the facet I, okay, so each facet. Again, as before, we have these portions of the sphere, right, that have some centers somewhere, right, the different centers. So this is also supported, right, by the different center. But I can still define the angle at which these two spheres meet. So still, I can define the angle between these two spheres at the edge, at every point on the edge. Right? So if I look at the radius here, right, at this point, and if I look at the radius here at this point, right, so this angle between the two normals of the spheres at this point, this gives me, I'm going to again denote it as by angle gamma, okay, similarly as before. So gamma here, this is the angle, and of course it depends on, now enumerating somehow ij, so the angle between two adjacent facets, the facet I and the facet j. So this is angle Okay. And another thing what I'm going to denote, I'm also going to denote the length of the edge. So let's say that these two spheres met here by this edge, so the part of some small circle. So this edge I'm going to define as the length of this, the edge between two adjacent faces. Okay? All right. So we didn't have really this parameter in our two case because really we were in a bit simpler case. So what we had just length of the circular arcs and the angle between where the two circles meet. Now we have a bit more complicated combinatorics here. So we will need this parameter too. Okay, so in this notation, as before, what's the surface area of the original one convex polytope? So the original one convex polytope is going to just consist of all these facets, and each facet has the area beta I. So as before, this is again going to be just the sum of all beta i's. Okay. Now, what's the area of the inner parallel bodies? I'm going to write it down and then I'm going to explain it, where this is coming from. So it's going to look similarly to what we had last time, and the idea is very similar, but the computation is a bit more complicated due to the fact that we have a bit more complicated combinatorics. So the idea here to obtain this formula is similar to what we had last time. So So in order to obtain the similar formula on the plane, we again had to step inside by this parameter t. Right? So we're going to do the same here. Let me focus on one. Okay, so something like this, right? Let's say that this is one facet, right? One portion of the sphere. So I'm going to step down by the parameter t along all the normals, right? So along all the normals again, so this sphere has somewhere the center, right? I'm stepping down by the normals, so I will get something similar, right? But now, of course, this is going to be the portion of the sphere of radius 1 minus t, right? So this is the portion of the sphere of radius 1 minus t, okay? Now, in fact, not this entire portion, again, contributes to the surface area of the inner parallel body. Because we step down by one facet inside, but we also will step down by another facet which is adjacent to it inside, or by this facet that is adjacent to it inside, right? So, in fact, for each of them, right, it's the similar story. Again, we would get the portion of the sphere that lies on the sphere of radius 1 minus t, but each of them are going to intersect now here, by, again, as before. So in fact, the portion of this blue part of the sphere that matters is going to be smaller. There's going to be some yellow part here, which actually contributes to the surface. Make sense? So, as before, right? Before we had the circles, and we had just the little tails, right? Here, this little tails now becomes some portions really of the sphere, right? Some spherical belts, in some sense. So, meaning what? Meaning if I want to compute the surface area of these guys, of the yellow portions, I can do the same thing. I can compute the surface area of blue portions, and now subtract what I have the outside, right? The parts where they intersect. The surface area of the blue portions, it's exactly the first term. Because we have the area of the white portion of the sphere is beta I. We have just the homothety, right? So, you can think about that the radius of this blue sphere is now 1 minus t. We in R3, so we have to do radius squared, right? Times the area of the facet. Okay? So this first term, it's really just the sum over all such blue portions. Okay? And now we need to subtract. You can guess that, again, this term will correspond to the term in T that we're subtracting here. So this shaded yellow part, right? Now, how I can think think about it? I can think about it again in the same way as before. So if I'm around vertex somewhere, I can justify that around the vertex, the area is really behave as t squared, and it doesn't really contribute to the first order terms. Before we had the similar story. Around the vertices, we had the behavior t squared, so it wasn't really contributing. And then really what contributes to, it's really the portion that corresponds to these edges here. But the portion that corresponds to the edges, it's really going to be something close to the rectangle on the sphere. So the rectangular part of the belt on the sphere. Okay? So if I look at this, if my t is very small, right, the same way as before. Last time we had if t is very small, I had the right triangle, right? Here, if I can think if t is very small, then really what I'm getting here is something close to the rectangle, and the rectangle of where one side is almost like the length of the original edge, and another side, so this kind of portion, it's exactly almost like the tail that we had in R2. Because if you kind of think about the two-dimensional picture, that's what it is. It's really almost like my tail there. So this portion was exactly of that order. So really, again, what contributes to the order, to the first order in T, it's really the portion along this which we subtract along the edge. The portion along the vertices, again, we can justify that it is of order t squared, so it doesn't matter. And what matters really the portion along these edges, and that's where we subtracted here this part. Again, we subtracted twice then because at each edge I have this portion, and I have the portion at the adjacent sphere that meets, which I also need to subtract. Okay? Make sense? So this is, again, I don't want to get into complications here, just doing specifically, because it's the same as D as before, but a bit more complicated in notations, just so that we have a bit more portions in the sphere that we need to deal with. So essentially, by kind of doing this argument here, we can get to the formula, right? Now the idea is, okay, so once I have the formula, I need to want to differentiate, and I want to find the derivative at 0, right? So I want to compare the derivative of 0 of k and the derivative of this thing at 0 of the length, right, corresponding length. So again, the idea here that if we show that the derivatives greater than the derivative corresponding to the derivative of the surface area of the length at 0, then we are done. So by the constraint that at the start we have the same surface areas, then the functions must also obey this inequality. So that's going to be good. So we need to differentiate. Okay, so let's differentiate. Then what is our derivative here? Okay, so we're taking the derivative at 0, right? So the first term gets the contribution only when we have t, right? So it's going to be minus twice the sum of all beta i's, right? If I expand, we just take the derivative there. So I have minus twice sum of beta i's, and the second part is minus twice sum of all this. And the tail again disappears. The tail is of higher order. And again, the similar story. So if you recall, in R2, we didn't have this part, so we didn't really have edges. So we had to minimize the following portion. Now we need to deal with this portion. And again, why I claim that we need to deal only with this portion, because the first part is really fixed, right? The first part is really, again, just the surface area, okay, right, which is the same as surface area overall. Okay? So what we really need to do, we really need to minimize this thing and show that it is minimal on the length. Right? Because I want to say that this is greater than the same expression for the length. Or in other words, if I take into account that minus sign, so what I want to actually maximize this sum. and show that it is maximal on this line. Okay? Make sense up to here? Okay, so now we need to do this maximization. So let's try to maximize. So as before, how do we maximize? So in order to maximize, I need to get some constraint under which I'm going to maximize. Now again, I'll go back to the two-dimensional case, because my idea, okay, I want to generalize it. So my first constraint was what in the R2? In R2 I said that my first constraint came from the fact that the spherical image of the convex curve is equal to 2 pi. Right? So I want to find something similar in R3. And what is something analogous in R3? It's exactly the Gauss-Bonnet theorem. So the Gauss-Bonnet theorem exactly tells me the spherical image of the boundary of the, in our case, of the body is going to be equal to the sphere, to this area of the sphere of radius 1. Right? So let's restate Gauss-Bonnet. So it states that over the boundary, if we integrate the Gauss curvature over the boundary of K, we get the area of the sphere. So here, this is the area measured on the boundary, and this is the quantity that we seen in the first lecture. So it's in some sense natural why we have the curvature here, because again, if I think about it in R2, what does it mean the spherical image of a curve is equal to 2 pi? It really also corresponds to the fact that the tangent angle rotates, along the curve by the angle 2 pi. And the way how the tangent angle rotates in R2 was corresponding to the curvature. So I could have wrote that condition as integral of the curvature is equal to 2 pi. Where here, this is the integral again of the curvature, but now the analog of the curvature in R3 here is our Gauss curvature, which is the product of both principal curvatures. And we have, it's equal to the area now again of the the sphere in R3, which is 4 pi. Okay. So I'm going to take this for now as for granted, and at the end I'm going to give intuition why something like this actually should hold. But for now, let me take this and let me apply it. Let's see that we can proceed, that we can actually deal with it if I have the Gauss-Bonnet. Because realistically, the way how it's written now, it's not really obvious where is so what this constraint here means, so what the left-hand side really means. So really I need to rewrite this left-hand side for my polytopes, right, for my one convex polytopes. So when I'm rewriting it, in my case, the polytope is not smooth anymore. So I have the portions, smooth portions, which corresponds to the spheres, but now I also have the edges and the vertices. So I would really need to integrate over the smooth parts where the curvature makes sense. And then I would need to integrate over the edges and over the vertices by computing the spherical image of the normals at each of this. So let's see. So let's say that for my one convex polytopes, what do I have? So how can I rewrite the left-hand side? So the boundary is not smooth. So the left-hand side, I will write the following. So if I integrate over the boundary here, so what do I get? So I will split integration over all the facets and sum over all, of course. So I have sum over all the facets. Here integrate over the facet, and I can write here the Gauss curvature honestly, because here this is just a portion of the sphere, and I even know what the Gauss curvature there is. Now I will need to integrate over the edges, and let me now put something here that corresponds to the edge, right? And then we will write what it is. And then I also need to integrate over the vertices. Again, let me put something here for vertices. So we are going to determine what those are for now. Okay? So now we need to compute these parts. The first part is easy. Here I have the Gauss curvature of the spheres of radius 1, right? So this is just the Gauss curvature is reciprocal of radius squared. So in this case, here is just 1. So what I'm doing, I'm just integrating the facet over the with respect to the area matter. So really, I'm just getting the area of each facet here. So this integral here, this is really just the area of each facet. Okay. This is good. Now, the portion that I have here, I claim that I'm not even going to actually compute it. So I have it here, it's present. But I need to know, I'm going to get lucky, and I actually just need to know about it that is greater or equal to 0. Because it is going to be greater or equal to 0. So if I have a vertex, at each vertex I have some normals. I want to look which these normals, which the region these normals span on the sphere, on the boundary of the sphere. But really, if I have a vertex, it's going to map there something. So it's going to be non-empty. So what I know here, I know that it is here, and I know that it is greater or equal to 0. So now let's deal with the edges part. For the edges part, we actually need to compute something. So now we need to compute these portions to these edges parts. So what do we have here? So in order to do that, again, let's think, what do we really need to compute? So if I have the, let's say, take some point on the boundary, okay? So if the boundary is nice, the boundary is smooth here, and I take the point. So what I have at this boundary, I have some normal vector, unique normal. Now if the boundary is not really smooth, so if I have some edge, so let's think about such little tent here. So if I have something like the edge here, and I take the point on the edge, then really I have many normals here, and these normals are really normals between the two normals to the facets on each side. So I will have the normal here, and normal here, and then all the normals in between also count as normal vectors at this point. Okay? And if I have a vertex, even more, right? Even somehow I can think about as a cone of all the normals around the vertex. So that's why let me think about the so-called normal form to be all normals, all outer normals at the point Z. Okay. Now, really, I need to think about the following. So I might not have to take only one point on the surface. I might need to look at some region on the surface and look at all the normals that corresponds to this region. So then I can say that, okay, if I have my K, right, let's say that I have some region here. Some region omega, okay, that lies on the sphere, on K. So omega lies here on the boundary. So then I can consider the following quantity. I'm going to call it U omega. So this is all outer normals at the points of this region. So all our outer normals at the region that lie now on the sphere, okay, on the unit sphere. All right? So this is so-called spherical image of this region. Okay, so we technically take all the normals that we have here and put them on the unit sphere. Okay, and start at with the center at the. Right, they all start at the center of the unit sphere. Okay, so now what these creatures here really are.
Are they cosines of half of gammas, or?
Well, almost. Yeah, they are going to be something like that. Yeah, you will. We will see what. Yeah.
I was just trying to compute it.
Yeah, yeah. Yeah, you need to really do the trigonometry there, and they're going to be related to gammas. Yeah, to half of the gammas. So now what we really need to compute. So when we compute in this portion, the portion that corresponds to the edges, this portion now really is just the spherical image, so the area of the spherical image of the edge on the sphere. So we take the edge of our polytope, we consider all its normals, we put them on the unit sphere, and we see what's the area there they fill, right? The portion that corresponds to the vertices here is the same story, but that corresponds to the vertex. So I take all the normals at the vertex, put them on the sphere, and see what they're going to, what area they're going to give me on the sphere. So this is really just the spherical measure here of the portion that corresponds to the spherical image of the edge, and divided with the vertices. This is again a measure, so the area, or in other words, the area on the sphere of these guys at the vertex. Okay, so as I said, I'm going to be lucky, and I will actually not need to compute this part, but I need to compute this part. So I need to compute the part with the edges. So let's see what the part with the edges gives me. So if I have the edge here, right? So this is the edge of my polytope. Okay. So I want to look at all its normals here, right? So the normals at the edge, right? Which, remember, the highest angle between these normals, that what we denoted was exactly the angle gamma, right? Or gamma ij to each, but let me simplify for now and just look at one situation at the gamma. So, and of course, right, I have to cover all the normals here in between them, right? So they all also play their role. Now, I want to map them all on the sphere, okay? So I have the sphere, and this is my equator. I want to map them on the sphere in such a way that, that they span some region here, right? I want to compute this region here. So how do I compute this region? Well, I can always introduce the spherical coordinates here. So I can think about the spherical coordinates phi theta, right? Such that phi is the angle that runs in the plane, right? And theta is the angle that runs like that. So I'm going to take this parameterization when theta changes between minus pi over 2 and pi over 2. I'm going to look at the picture, so where's the theta changes? Theta changes, so if I want to make the picture look symmetric here around the equator, so the theta really changes from minus gamma over 2 to gamma over 2. It has to span this entire interval at each. Yeah, no, okay. Okay, so this is going to be a circus performance, okay? All right.
But it was quite impressive.
That was impressive. Even for me. Okay, so Yes. Because it's 9:30 in the morning, you know, everyone has to wake up, yeah? Okay, so, right, so I need to parameterize this region, right, at this normal span. So at every site here, where theta, right, at every point where I'm looking at this normals, the theta is going to change between minus gamma 2 to gamma over 2, right? So spanning this angle. So this yellow region right here, I can say that gamma over 2, okay? And I need to know how phi changes. Well, again, I can always make it in such a way that it changes from angle 0, right, up to what? Up to really, I need to know what the angle supports this edge here. So what the angle supporting there. And if I do some trigonometry, I can show that the angle, which it does, it's exactly the length of the edge over this cosine of gamma over 2. So this is going to be the angle here that is this small circle supported on each sphere, which I intersect. Okay? So this is my region. So I have some region here. This is the region that I can parameterize, and I want to find its area. Okay? So how do I compute the area? So, okay, so the area is exactly going to be this guy on the edge here. So I need to integrate, right? So I integrate the area on the sphere. So I integrate over phi. I integrate over theta. Now here I need to put the Jacobian on the spherical coordinate. And so the way how I choose the parameterization here, the Jacobian is going to be cosine. So it would have been sine if I did theta from 0 to 2 pi. So here I have cosine of theta, and I integrate theta d phi. And now magic happens. So when I integrate over phi, I can integrate immediately. It doesn't depend on the theta. When I integrate over theta, so here I really have sine like this, which gives me twice L sine of gamma over 2 over cos of gamma, which is tangent, which is exactly the tangent gamma over 2. Okay? And what happens here is that we get very lucky. Because if I look at this term now, and let me plug it back into here, into the Gauss-Bonnet formula, right? So let me combine everything. So if I combine everything, what do I get? So I get that this integral here, right, this sum of all the areas of the facets, the sum of beta i's. Then I have the sum of all the areas, all such areas over all the edges. Again, if I enumerate my edges as before, I can write that this is 2 times tangent of the angles over 2. Right? For each of them, they correspond equal to this area for the corresponding gammas and edges. And I say that I keep the portion with the vertices. Okay, I'm not going to compute the vertices. So here I have the portion with the vertices, and this is all must be equal to 4 pi. Okay? So this is the constraint that I get from the Gauss-Bonnet. Now, luckily enough, the function, I already erased it, right? But the function that we need to maximize, it's actually exactly precisely this function that appears here in the constraint. So let me rewrite this a bit, okay? So let me keep this function on the left, up to 2, it doesn't matter. Tangents. Right. And I will rewrite it a bit. So I'll have 4 pi minus sum of all beta i's. What the sum of all beta i's is? This is exactly as before, just the area of K, the surface area of K. So here is K. And then I have minus portions of this guy over the vertices. So this is fixed. This is also fixed, because this is the same as the length. This doesn't change. Right? And what do I have here? As I said, the only portion that I needed here, I only needed to know that this is some spherical image of some of the normal points at the vertices. So there, these things are greater or equal to 0, and when this right-hand side, when this function is maximal. This function is maximal exactly when this contribution is just a 0 contribution. Yeah, but what is the when do I get the 0 contribution? I get the 0 contribution where there are no vertices at all. And I'm dealing with the intersection of balls. So what is the intersection of balls for which there is no vertices? Well, it happens that this is exactly only with the length. So this thing is equal to 0 only on the length L, right? Only the length that length doesn't have vertices. Okay? And we are done. So this is telling me that, okay, the function that I wanted to optimize, right, the function that I wanted to maximize is maximal exactly on the length, which tells me that the proposition for the functions, for the surface area functions, also that the surface area of the inner parallel body is also always greater than the surface area of the inner parallel body of the length. And we're, as from the last time, we are completely done, right? So that's exactly, we can complete the last step, it's the same as yesterday. So we take K, here we integrate over the surfaces of K, of the inner parallel bodies of K. They each pointwise related to the surfaces of L, which is exactly the volume of L. And again, as before, here, if I have the proposition that this guy is greater than this and the entire interval from 0 to R of K, then R of K has to be greater than R of L, so I can replace it.
So is this the point where you get into trouble in higher dimension?
Yes, and this is the point where I get into trouble in higher dimension. So,
Why you got trouble in higher dimension?
well, so in higher dimension, I'm not getting this lucky. So I can I can get the similar to the Gauss-Bonnet, right? I can also say that the spherical image of the convex body is equal to the area of the higher dimensional sphere. That is okay. And I can still, with a bit more complication, but the formulas for the surface of KT is going to look similar too. So again, the same story. But then I'm not getting lucky that the function that I need to optimize is not anymore so easily appears in the constraint that we have. And then it turns out, well, if you maybe do some numerics or computations, it turns out that it kind of doesn't give you the constraint anymore. So it sits somewhere in between. It doesn't tell you that it's wrong, but it also doesn't help you really. It doesn't really help give the constraint. So in some sense, in R4, let's say, even in R4, I don't know where to get the right constraint. Clearly that this is already not enough. It doesn't just give the constraint anymore.
Are there any other constraints which you could use, as in the case of 2 dimensions?
Yeah, you can also do the similar constraints in 2 dimension on the angles. And you can do the similar constraint, well, now by analogy, for the lenses, let's say, of the edges. But again, they do not seem to help. It doesn't seem that that is enough. So something else is clearly missing there in this approach. But up to this point, after the optimization part, everything, in some sense, everything can be done. And big portion of it even can be done in Rn without any trouble. But for this proposition, I really don't know how to push this proposition through to higher dimensions. So that's the issue in what happens in Rn, or even in R4, right? Even R isn't it? Okay.
So you don't get the tangent gamma half, or what's
No. Yeah, the function that you need to minimize is going to be of this sort again. Mm-hmm. But yes, in the constraint you don't get this. I don't remember there, but it's something some sine squared over cos or something like that, with the L's and with whatever the areas are. So that's the issue here. That's the problem. What happens here? Okay. So, let me to finish, let me mention, go back here to the Gauss-Bonnet and quickly give the intuition why Gauss-Bonnet really holds here. So, I do not have time to prove it completely. many tools to introduce, but so the only thing which is left is kind of, I'm going to talk about heuristics, why the Gauss-Bonnet in general, why something like Gauss-Bonnet should hold. So, let's say the idea. So, let's start with something simple, okay? So let's start with the sphere, and let's say that I have the sphere of radius r. This is the radius. So on the sphere, I can look at the so-called balloon, so the region that is bounded by two great circles. So if I look at the one great circle, it's over here, and look at the other great circle, this is the region, the so-called balloon. And this, let's say that this balloon is supported by, so the angle between these two circles, big circles, is just the angle theta. So the angle between two circles is the same as the angle between the planes that they contain in. So one can show, just by setting up the proportion, that the area of a balloon, in this case, is just twice the angle times the radius squared. Now I can change the picture a bit. So now instead of looking at the balloon, I'm going to look at the triangle in the sphere. So I'm going to find the intersection of three big circles instead of two. So if I look at the intersection here of the three circles, so how do I want to? So let's say that this is one. Now let's say that this is another, and let's say also. Okay. So I have the triangle here that is bounded by blue, white, and yellow big circle, okay? So let's say that in this triangle, so what I have this is alpha, this is beta, and this is gamma. So each two circles meet at a certain angle. And let's say that A corresponds to the area of this triangle. Okay? Now I want to write some relation corresponding to this area of the triangle. So when I look at these three big circles, I can see that they split the entire sphere into 6 looms. So forget for now about triangle. So each of them, right, I have like a piece of mandarin, right, if you want to pick it up here. And each of these looms is going to contain one copy of this triangle. So for example, this loom that is bounded by blue and white curve in here contains this triangle. There's going to be another one at the back, so by symmetry on the sphere. There's going to be such triangle, but here at the back. And there's going to be such loon at the back too. It's going to contain that copy of the triangle, and so on. So each of these loons contain one copy of the triangle. So in total, if I try to sum up their areas, I should get the area of the sphere. Right? So let's sum them up. So what I get, I will write as follows. I will say that I take into account 2 areas of this triangle, one at the front and one at the back. Okay? Now I should take the area twice the area of this loon and subtract twice the area of the triangle from there, because each loon contains the triangle. So I will have twice area of the loon minus area of the triangle. Okay? But then the same I should repeat for each of such loons, right? So now I can take plus twice the area, let's say of beta, right, with blue and yellow. So beta minus area and plus twice minus area. Okay? So this should be equal to 4 pi r squared. Okay? So this in total should equal to the area of the sphere. Now I can simplify. So I can cancel something on the left, and I'm going to also divide by 4 r squared. So what I'm going to get left on the left here, it's going to be minus area times 1 over r squared, and here I'm going to get 5. Okay. So really what I'm I'm getting here, I'm getting the relation on the sum of angles of the spherical triangle. Now, what appears here in our in our understanding, what is here is just the Gauss curvature of the sphere. So here the sphere has the constant radius r, 1 over r squared. It is the Gauss curvature of the sphere, right? And I can write this as alpha plus beta plus gamma times kappa is equal to pi. Okay? So this is the simplest case. Now, let me take this formula and apply it a bit more general situation. So now let me look at something more general. So let's say now that I have surface, let's say that it's not necessarily the surface of the sphere, but let's say that I have a surface which I can triangulate with some spherical triangles. Well, similar to my polytopes, but maybe of course they don't have to intersect only, the faces doesn't have to be only triangles, but let's think that if I can have the triangles. So if I can have the triangles, then what I can do the similar thing. So I can apply this type of the formula for each of the triangle and sum them up. Okay? So if I enumerate them, let me sum them up. On the left, I have the sum of the angles. On the right, I will have here pi minus each area on each curvature. And then I sum up over all such triangles, over all their angles. So alpha 2, and here I have then minus kappa. Okay. So when I'm summing up, what I also know, if I'm in this case, that if I fix a vertex here around the sum of the angles around which each vertex should be summed up to 2 pi. So, in fact, what I can do, I can rearrange the left-hand side and kind of group all the angles that lie at every vertex. So if I group such angles, then I will have the number of, the left-hand side is just equal to the number of vertices multiplied by 2 pi. It's the same thing. What I have on the right-hand side then, I have phi multiplied on the number of such triangles I have, so let's denote them F capital, the number of facets. Okay, and I'm subtracting here. I shouldn't subtract right to that. I need to move in that formula A to the right. So then I add all this thing and then in this case, what does this really represent? Let me write it down and then I will say why. So we have pi times the number of facets times really what is written here is the average of the Gauss curvature over our surface. So one way to think about it, if it's written this way, one can think about it, it's kind of analogy of the Riemann sum in some sense here. Or one can divide and multiply by the total area, which is just the sum of all this A1, AN. And you can see that I'm going to take the average curvature with respect to the area of the entire surface. So in some sense, what is here, it's kind of like the integral over the curvature over the boundary of the surface. And then what it is exactly the Gauss-Bonnet here. So this integral is exactly the integral in Gauss-Bonnet. And the left-hand side, so if I move all these things to the left, and let's even divide by 2 pi, so here this my integral of Gauss curvature, and the left-hand side, one can show that this is just earlier characteristic of the surface. So this is some. Now, the beautiful way of this formula that the right-hand side here really doesn't depend on the combinatorics of this surface at all, while the left-hand side really doesn't depend on the curvature of the geometry in some sense. So it's really two notions that are related by this beautiful de Gauss-Bonnet theorem. Now, what is here, right? Here it's in some sense the formula when I have the constant Gauss curvatures at each triangle. But this is kind of the hint why one can believe that something like this might happen, should be believable that something like this should happen for the general surface too. Okay, so this is kind of the rough idea behind why the Gauss curvature, or why the Gauss-Bonnet, something like Gauss-Bonnet theorem should hold. And I'm going to stop here. Thanks.